Okay, السلام عليكم. Can you hear me all يا شباب?
Yes, yes.
Okay. Okay, welcome back. I wish you had a good, enjoyable weekend. And before I get started, I would like to remind you that I have uploaded the homework number 1, and as well as chapter 3 of the book is now available for you until you get the textbook for those who still didn't get them. Also, I would like to remind you that we will have a quiz this Tuesday. It's going to cover the material until what we finished today, which is an introduction about bending stress. The quiz, as I told the other section, is going to be probably multiple choices, but I will ask you to upload the solution, combining the answers, okay? So I would really highly advise you to make sure that your setup is ready. So are you going to take a picture with your phone and then transfer it to your computer, and from your computer to the blackboard? Are you going to do it right away through the blackboard? What kind of app you will use? Are you going to use a scanner app, or are you going to use a hardware scanner? It's up to you. I may try by tomorrow to put a sample test for you to examine your method, you get familiar with it, because what I'm going to do, I will calculate the time necessary for the quiz. Let's say it is 15 minutes, and then I will give you additional 2 minutes for uploading the attachment. So you should be trained and you should know what you are doing, okay? With no further delay, let's get started. Within 10 to 15 minutes, what I'm going to do, I will share the attendance sheet screen with you. And what I want, in the first class, I asked the student to switch on their video camera. And it seems like there was a little bit of confusion. So what I would like you to do, to look at the screen when you feel that your name is the next one, or the one after the next 2 or something. Try to get your camera ready. So we have little, because people were saying, I'm here, and I don't see their picture. It's not coming to me. So we'll see until we get used to it. It's taking too long, but hopefully within the next weeks, it will get easier and better. Okay, Akhwan? All right. So last class, we stopped right there. Actually, we stopped in here when we talked about stress. And we said that stress is a field, and it is mathematically, it's a tensor, it's not a vector. And we said that it's probably the best way to describe a stress is by a surface. And whenever there is a surface, you cannot just point on a value of the surface without telling me where on the surface do you want me to measure it. And this is pretty much what stress is all about. So again, just to remind you, stress is the measure of the internal forces acting within a deformable body. The unit of stress is the unit of force divided by unit of area, which is in Newton meter square, which is usually Pascal. And not usually, it's just Pascal. What I was planning to say is that we usually measure stresses in megapascal, and most of the time we measure like values like modulus of elasticity, which is measured in stress, is in gigapascal, because they are more huge compared to, especially for metals. But you are all familiar with the unit system. Now, so to summarize, now, what are we going to talk about next is the normal stress. So what is the normal stress? It's a state at which the stress field acts normal. See, stress field, don't forget, and it acts normal to a given plane. So whenever you have a plane, any plane, all right, and there is a stress which is normal. So we call, if there is a stress acting on this plane, we call it normal stress. If there is a stress acting on this plane, we call normal stress. And if you remember, we used to plot the cube, and we said that sometimes there is a shear stress, which we represented this way. Now, of course, many times we are not going to put too many arrows just to waste the time and make me tired trying to convince you that this is a field. It's always a field. We represent it by one arrow. Okay? Now, this is shear stress. Interestingly, ya akhwan, that all of the kind of deformation you can imagine. If you take a cheese, a block of cheese, and you deform it the way you want, or you take dough, which is ajeen, and you form it like a pizza, like a sandwich, it doesn't matter. All kind of loads that you put on that can be described by normal and shear stresses, which is very interesting. Accordingly, since you change the shape of the object, the deformation that happened, which is measured as strain, is also shear and normal. Very interesting. Everything possible. Just like when we taught you in dynamics. In dynamics, what did we tell you? We tell you that there is a translation, there is rotation. If you combine them, you get general plane motion. Everything moves on this planet, everywhere in the universe, can be described by these two combinations. Very nice. Now, so you should know that we have normal and we have shear stresses. What we are talking about now is the normal stresses. So they are always normal, act normal to a given surface, plane, okay? Now, this is an illustration. What you see is a force P applied on a surface in tension, and this is the same force but is applied in compression. Now, tension, compression, they are both normal. They will create normal stresses. The only difference is their effect. The deformation resulting from a normal stress is going to be extension. The part will become longer, and the compression will cause the part to get shorter. Now, what I would like to tell you is that this representation of a cube with one arrow, two arrows, is very important and critical. I don't want to confuse you, but I want to give you a little bit of, illustration on what does this mean. And it will also answer a very interesting question I raised before about why are we dealing only with stresses. This cube is an infinitesimal volume. Infinitesimal volume means it is a representation of a little tiny, if you imagine that this is the specimen, the stress strain tension specimen that you break in the material science lab. The volume is sitting right there on the surface, and it is really tiny. It's just a manifestation of the limit when the delta volume approaches zero, not infinity, sorry. So it doesn't go to zero, but it approaches zero. So that little tiny cube, if you have a tension like this case, you will have a cube which is having one arrow pointing in the same direction as the force. Now, if for any reason you applied another load, you will get another arrow. You may get another arrow. Now, if we have three arrows, this is a triaxial state. Tri means ثلاثة يا أخوان, three. So this become a little bit difficult, not easy. You need to study matrices. You need to go back to the origin of the stress as a tensor. For that reason, we only do three-dimensional state in graduate courses. But within your undergrad, the maximum we go to is 2, which is a plane problem. So if you apply one stress, you'll get one stress. If you apply 2, you get 2. If you apply 3, you get 3. And you tell me, okay, what is so fancy about this? We know this. And I tell you, if you do strain, it's totally different. In strain, ya shabab, if you apply one normal strain, there are other strains that are going to be generated. And inherently, strain state is triaxial. That's why it doesn't make sense to teach you strain here. That's to answer a question I raised before. Why are we dealing with stresses? We're not dealing with strains. This is probably one of the reasons. So, one tension, one compression, both of them are normal. And what you should know is that normal stress can also be generated using a totally different creature, which is the bending moment. Now, in here, look carefully. If you look at this cross-section, what you see is that the arrows are pointing. I mean, if I do it this way, the arrow is perpendicular to the surface. So this is a normal stress. The only distinct feature about bending is that it creates tension and compression, both in the same cross-section. But both of them are perpendicular to the surface, so they are normal stresses. So indeed, okay, the difference between a force like this and is that this will create a constant normal stress. Everywhere here, okay, the value of the stress is, let's say, 10 megapascal. Everywhere. This point, this point, this point, this point, all points have the same value. So this is like an equation, y equals to a constant, right? Or x equals to a constant, depending on how do you look at it. Now, in here, no. This is like y equals to ax plus c. It's a linear distribution. Now, what we are interested in is that this distribution, we call it what? No, uniform distribution. This is uniform. It doesn't mean that it has to be constant. And it can be described mathematically by relations, equation. I am not talking about a cross-section which has a stress distribution like this, where the stress is randomly changing in a different way. No, this can be described mathematically. That's why we call it a uniform distribution, okay? Now, so what you learned so far is that the normal stress generated by bending is transiting from being positive to negative, and at one certain point, if mathematically, ya shabab, if there is an equation which has a value that is positive somewhere and then the negative somewhere, okay, it will pass through zero. It must. So this is what happened with the stress, which is this line, known as the neutral surface. Okay, let me stop here the recording. I don't need to record this. Actually, I do. Leave it. What I'm gonna do, let me share the screen with you. Get ready, ya shabab. The first one and the second one, at least, and I'm gonna show you the list soon. And then I want the first and the second in the list to turn on their cameras and so on, or maybe the first 3 students. And then once I call your name and I tell you, okay, we go to the next one. So when I call your name, you can just switch it off again. Okay, you don't need to turn it on. Can you please turn on your webcams يا شباب, the first three? So Hussein?
Yes.
Where are you? Okay. What's your family name?
أبو الرحي.
أبو الرحي. Okay. حياك الله يا حسن. صالح؟ سعيد؟
Yes.
Where are you, صالح? Okay. حياك الله يا صالح. عدنان؟ Yeah, I see you يا عدنان. Good. المدن؟ محمد؟
Yes, sir.
Okay, good. صالح؟ سلطان؟ Sultan, where are you? Ali? Toelib?
Yes.
Toelib is here. Saleh, I can see you. Where are you?
Yes, doctor.
Okay. Walid Al-Amri?
Yes.
حياك الله وليد. فيصل؟
لحظة دقيقة يا دكتور، بس عشان أسمح للدخول الكاميرا. الدكتور يقول لازم أطلع وأرجع أدخل خلاص عشان يسمح الكاميرا تشتغل.
Who are you? You're فيصل؟
فيصل عطوي. أيوه.
عطوي. It's okay for today. Tomorrow, next time you get ready, okay? البلوي علي؟
Yes, دكتور.
Okay. محمد؟
Yes, doctor.
The boss.
Yes.
I cannot see you yet. Okay, I see you now. مفلح?
Yes, doctor.
دوسري?
Yes.
You are not coming yet. Okay, مفلح, I can see you. Okay, good. فهد?
Yes.
فيصل؟
Yes, doctor.
حياك الله يا فيصل. مصلح؟
Yes, doctor.
Okay. سلمان؟
Yes, doctor.
فارس؟
Yes.
Okay. خالد؟
Yes, doctor.
سعد؟
Yes.
سعد. Where are you, سعد? سعد. I can see you. You are mute. عمر مالكي.
Yes, doctor.
Okay. علي معراج.
Yes, موجود.
Okay. ثامر طوع.
Yes, doctor.
مصطفى نويسير.
Yes, doctor. Here.
مصطفى. Okay. مصطفى جاسم صح؟
Yes. Yes.
Okay. فواز العوفي.
Yes, doctor.
Okay. أمجد.
Yes, doctor, here.
فيصل.
Yes, doctor. Here.
I still can't see you. يا فيصل. Okay.
Yes.
Yeah, okay, good. محمد.
Yes.
Okay. ناصر.
Yes, doctor.
Okay. عبد الرحمن. عبد الرحمن. Yeah, I can see you. عمر.
Yes.
عمر, where are you?
Yes.
I still don't see you. Can you talk?
Yes. Hello.
I can hear you, but I cannot see you. I don't know why. Oh. Okay. لا أنت مؤيد. We'll let you pass this time يا عمر.
أنا مشغل الكاميرا الحين يا دكتور ما أدري ليش.
Okay. I got you. بديوي. مؤيد.
Yes.
and Muhammad.
Yes, doctor.
Okay, thank you so much. خلاص يا شباب, you can switch it off. This is yeah, Mi'raj. Who is he? Who just got in? Okay, yeah, Juan, I want you to make this easy for everybody here, okay? So one way probably to do this, the first thing, we need to do a few maintenance over here. First, you should put your name in a way, with your ID it's beautiful, but maybe you want to write your name exactly the same way as it shows up in the blackboard. I can recognize you faster. That's number one. Number two, I can see that some of you are putting their photo, just like myself. You can see myself, right? This is going to make it much easier also. So maybe you want to go play with your account and try to do that. Do you understand, ya shabab? This is wasting a lot of time, but we have no choice.
Can you repeat, Doctor? What did you mean?
What I mean is that you're probably better off writing your name as it appears to me in the same way as it is in the blackboard. Okay, that's number one. Number two, do you see my picture? My name, before my name, there is my picture, right? My photo. If every student changed their photo, because now you are Faisal automatically is written in a green box with FA, the first two letters of your name. But if you put your own personal photo, it will make it easy, especially as we move on in the term. I can, even if you didn't talk like today, I can spot you quickly. Did you get me?
Yes, it's clear, Doctor.
Okay. Now, so let's move on. Now, with respect to the stresses, the interesting question would be, can we add them? If you ask the question, can we add stresses? That question cannot be answered. We cannot answer that. You should ask back, what stresses do you want me to add? Because you cannot add normal to shear stress. You cannot. خلاص انتهينا. There is no way you can add them. So normal stresses, you can add them together. Why? They are the same animals, the same species, the same creatures, if you want to call them. If they are positive, they add to each other. If they are opposite to each other, they cancel each other. The way we add them, as you see in the example here, is very simple. For example, if this one is, if this one is 10 megapascal, then every point in the cross-section has a stress of 10 megapascal. But this one, the normal distribution because of bending, might have a maximum value here of, let's say, 5 megapascal. And then, which is negative. And down, there is positive 5 megapascal. Now, clearly, you will go down until you reach the middle where the stress is 0. So if you go to the middle and you add this stress with this one in the middle, you will get a value which is equal to what? 10, because 10 is added to 0. But in here, you have 10 megapascal minus 5 megapascal. So this one will be 5 megapascal. Why? You have a positive 10 minus 5, then you have a positive 5. Down, you have 10 plus 5, it gets bigger, it becomes 15, and so on. Do you understand? You have to add them one by one. So it doesn't matter. If you have a cross-section And the same cross-section subjected to tension. Tension will cause a uniform stress that has a value of the same magnitude everywhere. And then you add bending. So bending is gonna cause compression in the top like this, tension in the bottom. And then if you add compression right there, let me make it with a green maybe, you will have a uniform compression. You can add this, with that, doesn't matter. But you add them one by one. One by one means this value, with this value, with this value. And then the next one, and the next one, and so on until the end. Did you get this? Is it clear, ya shabab? Any question? Okay. Hopefully this is a good warm-up for you. Why? Because we're gonna go to the bending. Now bending, ya akhwan, from the end, okay, let me remind you, is the famous, described by the famous equation sigma equals to mc over r. Now this is simple equation, came from lots of assumptions, but the beam is subjected to pure bending, no shear, no torsion, no axial loading. The material isotropic and homogeneous, it obeys Hooke's law. The cross-section remains straight and it doesn't change, and so on. Many of these assumptions in real life doesn't hold, but this equation still gives us a good approximation, actually very excellent approximation. So that's why this equation is used a lot. The reason why does it work, especially in mechanics here of, design, is the fact that when we design thing يا اخوان الحين مره من المرات يعني شباب تعرفون برج خليفه صح؟ ف مره شفتوا صوره ولا وانتم في دبي وقفتوا كذا وهب هواء وشفتوا البرج الانتانه حق البرج نزل للارض وبعدين رجع ثانيه تقولون ايه ويند it's to formation. No way. The idea is that when we do design, most of the time we operate, if you remember the stress strain curve is like this, right? Most of the time we operate here. I mean, in some situation, we can reach the yield. But in most of the time, we are operating in the elastic region. So when things are elastic, if you have a beam sitting on two supports and then you apply bending to it in the elastic regime, this beam will deform very slightly in a way you may not even see it with your eye. So that's why those assumptions are still valid. But if you deform something really, really significantly, then yeah, those values generated by this equation may not stand and hold. They will not be correct. Now, here we need to spend a little bit of a good time. Actually, we will spend probably the next 15 minutes or something in this slide or in the next one maximum. So I need you to focus with me. Now, the first rule we need to teach you about bending is that while the loading is happening in what we can feel like in one plane, the stresses are generated in different planes. So let me teach you what does this mean. First, before we do that, we need to put a coordinate system. Now listen to me carefully. The coordinate system that we will agree to use, all of us, always, is a right-handed Cartesian coordinate system. What does right-handed coordinate system is this? If you recall from the orientation, they taught you how to multiply unit vector cross product. They told you that if you multiply I by j, you get positive k. If you multiply j by k, you get positive I, and so on. So what are we going to do? The first rule that we are going to do is, this is a rule. It can be changed, but most of the time, like 99%, we are going to put the x-axis normal to the cross-section, just like in this picture. So if I look into this cross-section, okay, and I try to represent it in 3D, okay, what you see over here is that right in the middle, we assume that this is the x direction. Now, it's not up to you if you want to do a right-handed coordinate system. What you do, you assume that this is going to be the positive y. This is the positive x. Now, where is z? That's the question. The z is going to come here, not the other way. Why? Because when you multiply I by j with your right hand, your thumb, تعرفون الثumb؟ الإبهام يا أخوان. Yes, your thumb is gonna point toward the z direction. Okay, that's a positive coordinate system. Now later you will see that if you use a positive coordinate system, it's gonna save you, because you can mess it up later, and if you change it, it will mess up your signs and so on. So stick with that. That's the first rule. Now, obviously, ya akhwan, if we assume that this is the positive x, we can see that the distribution over here is coming like this as what? As positive in the x direction. So this is a sigma x. And right on top, we have the negative. Now the question is this: if I tell you that this is sigma x, okay, how did I generate it? If you this cross-section belongs to this. Now, of course, right in the middle over here, we have the neutral axis, or as it is named in the slide, the neutral surface. Why? Because now if you draw it in 3D, it's an entire surface. Good? So how did I generate the normal stress? I multiplied m, which is this one. So what is this m? Is it mx? Is it my? Is it mz?
I think MZ.
It is Z.
What?
Z.
It is z.
MZ.
It is mz. So why is that? Because if I look over here, I can see that the normal here is the x direction, there is going to be the y, and here is going to be the z. So if I put my hand rule again and rotate in the same sense as m, the thumb will point toward a z. So it is actually a positive mz. Good. Okay. Now, let's move on. The next part is what? Is the C, which is actually, ya shabab, C is the distance from the neutral axis all the way. Do you know what do we call this line? We call it a fiber. This line is also a fiber. So we say that C is the distance from the neutral axis to the top fiber or the bottom one, depending on where do you want to calculate the stress. Do you want to calculate it in here, or do you want to calculate it in here? We can call this one C1, we can call this one C2, because they are different. If they are the same, when the neutral axis is in the middle, then it doesn't matter, we just call them C. But in reality, shabab, in reality, if you want to know the distance here, this is what? Y, X, or Z?
Y.
It's Y.
Y.
And this one is positive Y, and this one is negative Y. Now, the real equation says that when you do this, you should multiply it by Y. Nobody can stop you. مثلا يا اخوان على سبيل المثال نفترض انه هنا في مشكلة في crack أو there is a hole or there is something and you want to know the stress there. You don't need to multiply it by C. You don't need to multiply by C1. No need. All what you need to do is to multiply by this distance. It's up to you. There is a stress there. Do you see it? So you can take any distance you want. The only reason why we are interested in C is because the maximum happened at either C1 or C2. That's the reason. But in reality, the real value of the variable here is Y. Now, if you look, in order to get a sigma X, we need mz and we need to multiply it by a Y value. Do you see that? Okay, now what is down here is another thing, which is the moment of inertia. Now, the moment of inertia هي نفسها لها subscript. YY, II, ZZ. Let's not talk about the II or YY or ZZ. Let's talk about moment of inertia. Moment of inertia is just like A. A, while A is measured in meter square, which is the area, okay? And moment of inertia is measured in meter to the fourth. It's a bit higher order than the area. Moment of inertia is associated with bending. And I am going to give you by the end of the class an example which will make it very easy for you to feel like that the moment of inertia is indeed related to bending. It can describe what is happening in bending. Now, I want one of you to tell me if we have a cross-section, which is rectangular cross-section, like this. And we will call this is N, and this one, we will call it M. Do you see that?
Yes.
Okay, okay. Now, what did I do? I will construct the positive coordinate system. That's Y and that's Z. And let's say, just like before, we had a moment mz, which is positive, by the way, because this moment, the thumb is pointing toward positive z, because negative z is here. Okay. Now, clearly, what will happen? المومنت يا شباب لو تفكروا فيها كما لو إن هي قاعدة it is stretching the material from the bottom like this, and it is squeezing or compressing the material from the top like this. So clearly, okay, this is the distribution, and somewhere in the middle, we will have the neutral line over here. Good? Are you good, ya akhwan?
Yes, good.
Yes.
Okay. Now, the question is this. Can anybody remember what is the moment of inertia for rectangle? What was it?
1 over 12 pH.
1 over 12?
Base times height.
Base multiplied by
the height.
Height Q. Now, those who said that the moment of inertia is BH cube, they need to be very careful. That's the reason why I call this one N and I call this one M. ما أبقاكم يا شباب تركزوا على الحروف. They are meaningless. And I'm going to show you in a minute that you can easily make a mistake over here. The question right now, within this, what is the base? What is the height?
It depends on the moment of inertia about which axis.
Okay, I give you a problem. You should know it. Which one is which one?
The base is N.
The
The height is N.
The base is N. The
height
height
is M.
M. Correct? Who thinks
Okay.
it is the other way around?
I think that you need to specify about the Y or about the Z. If I remember correctly.
So, يا فارس, do you think this is wrong? السؤال ما واضح. المومنت أعطيناك إياها, والدايمنشن أعطيناك إياها, والكوردينيت أعطيناك إياها. الحين أنت اعتبر نفسك في exam. Which one is the base? Which one is the height? If you ask me in the exam, you tell me, is this a complete question? I will tell you yes. I will not give you further information. عمر.
I think this is correct for IXX only.
عمر, السؤال سهل. Is this correct equation or what?
Yes, I think.
I think it's not.
Yes.
Those who says إنها هي yes. ليش؟ ليه مو بالعكس؟ ليه مو مثلا ال height is N والbase is M? Why not?
Because the N,
Yes.
The moment about
the
it.
parabolic to the Z axis, and if it's perpendicular is the height.
Doctor, with respect to the natural point.
Yeah. The actual definition of the base is that it is parallel to the neutral line. So the first step that you will do when you determine the moment of inertia is to imagine what would the moment do. And then by knowing that the neutral line is here, this dimension became the base. وعلى طول الدايمنشن اللي عامودي عليه ايش راح يكون؟ راح يكون الهايت.
Height.
For that reason, if we attempt the same problem again, okay? And then this time, while we have X, Y, and Z, this time I applied the moment along the Y. So this is MY. And it is positive, by the way. The thumb will point up. So it's a positive MY. Now look what will happen. Right here, there will be tension. The last fiber, الفايبر اللي عند الN. Over here, there will be compression. طيب, where is the neutral line? The neutral line is going to be right there. Now, if this is the neutral line, احنا قلنا هذا M وهذا N. Now, I equals to 1/12 the base by the height cubed. Where is the height right now?
N.
It is N.
It is N. And the base is M. Do you get this? Now
Yes,
look
yes.
what is interesting. Look what is interesting. The equation is still sigma x. Why? These stresses are pointing toward x. So I have an equation which says that my, and then what is this distance? What is it? It is Z. Yes, it is Z divided by I. And this I is measured like that. Did you get it, ya akhwan?
Yes.
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 Okay. Now, let me tell you this, thought experiment. Now, what happened is this. If you take a ruler, which, most of the time, if you go to a stationary, rulers have a cross-section like this. Am I right? But I'm going to assume that you found a ruler which is completely rectangular in cross-section. Now, this is the ruler. It's very long. Let's say 30 centimeter. These are the grids. And the question comes like this. If you give this ruler to a kid and you tell the kid, bend it, the kid will bend it along this line. And of course, the ruler will bend. Is that true? Kid,
Yes.
عمره 3 سنوات. He will bend it. However, I dare you to name one human being that can bend it along this line. Shabab, I said human being. I'm not talking about the Avengers, huh? No movies, no fantasies. Give me a name of a real person who can bend it this way. No, I don't think. Nobody. It's just so hard. You need a machine. Now, the only reason for this is moment of inertia. If you look, ya akhwan, what will happen? The moment of inertia will have 1 over 12 in both. You will calculate the moment of inertia in red, and you will calculate the moment of inertia in blue, in green. Both of them will have the same 1 over 12. The problem is not with the base. The problem is with the height. Here, I should have wrote this in green. Here, the height in green is very small number. For that reason, if you cube a small number, you get a small moment of inertia. But the height in the red one is large. And you cube it, and it gets even larger. Do you see that? Do you understand?
Yes.
So the idea here is that you will need, let me see. Did I reverse them?
Yes, Doctor, you reversed them.
Yeah, I reversed them. The green should be the blue, the red, and the red should be the green.
Yes.
Why? Because the idea is that how much stresses you will generate. Oh, I should. How much stresses you will generate, ya akhwan, in order to get the ruler bent. I in the equation MC over I is in the denominator. If you divide by a big I, you will generate stresses, high stresses quickly, and that's how you bend it. But if I is too little, okay, you will have a sigma which is big, which means that you will generate high. You will have to put too much stresses in order to bend the ruler. So before I end the lecture, ya akhwan, I want you to understand one thing over here, is that what is important is to construct the coordinate system, the right-handed coordinate system. You identify from the sense of the moment, where is the neutral axis? Where is the positive? Where is the negative? And then you'd identify the neutral axis. And after that, you know what is the base, what is the height, and that's how you calculate I. بالنسبة ل M, it's very simple. You know it from the load is given to you. Is it positive, negative? And there are two methods to deal with positive and negative. Is this positive? Is this negative? Either by inspection, you inspect the problem, which I'm going to teach you, or by equation. By equation يعني معناها انك تعرف the sign of M and the sign of C. Is it positive? Is it negative? Is it a positive Y, negative Y? In that way, you will have negative become positive, or positive negative become negative. We'll talk about this inshallah in the next class. Okay, thank you so much, everyone.